All right, we're going to talk about translating axes now. Remember from statics, using vectors, we could suggest that there's a vector A and a vector B, and the difference between them was considered B minus A. So if you want to go from A to B, you have to go through B minus A. And the vector equation would suggest that A plus B minus A equals B. Well, in dynamics, we call B minus A B with respect to A, and we put it into a little fraction like that. B over A or B slash A is B with respect to A. So for position, again, we would suggest we go from A plus B with respect to A equals B. So A plus B with respect to A equals B. In velocity, we do something similar, and we can take the time derivatives of those positions, and we can say that the velocity of A plus the velocity of B with respect to A equals the velocity of B. So we'll get used to adding velocity vectors in this way. We usually write the equation, the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. So that's the way we'll begin our analysis. Velocity of B is equal to the velocity of A plus the velocity of B with respect to A. And the way we kind of interpret this, again, there's a little fraction that kind of looks like if that's in the numerator, that's in the denominator. They kind of cancel. It doesn't really work that way, but that'll help you keep from putting on this side of the equation velocity of A with respect to B. That would make the signs messed up. So make sure that if you have the velocity of A on this side of the equation, that it is in the denominator there. Now, how do we interpret that? The way I kind of look at this is the velocity of B if I'm standing on A. The velocity of B if I'm standing on A. So the velocity of B with respect to A says if I am A, what does B look like to me? So again, we'll look at some examples and make sure we understand the with respect to's. All right, so here's a very simple example of relative velocity and position. Let's say that you can throw a baseball 50 miles per hour. And if you're on the ground, you throw the baseball, it's 50 miles an hour relative to the ground. However, if you're moving in a car, and the car is moving 50 miles an hour, and you're throwing the baseball 50 miles an hour, what you're throwing it is relative to the car. And so you can say that the actual speed of the baseball is the velocity of the ball, is the velocity of the car, plus the velocity with respect to the velocity of the ball with respect to the car. And you add them up, and you can intuitively know that it's 100 miles an hour, that you can throw, that the actual speed of the baseball is added those velocities together. When velocities are in a line like that, it's pretty easy to see. Same thing if you're throwing it backwards. Let's say the velocity of the car is going this way, and you can still throw the baseball relative to the car 50 miles an hour. When you look at the actual speed of the ball, it's the velocity of the car in a positive direction plus the velocity of the ball with respect to car, which is in the negative direction. You add those together and it's zero. So if anybody's ever tried that, throwing a ball from a moving car, the ball looks like it's going nowhere. It goes straight down, really, because the velocity relative to the ground would be zero. If you're going in say again, you're going in the car going in the x direction, and you throw the ball with respect to the car in the j direction, then we would add those two together vectorially, and we would have I and j components. And then we'd say that the actual velocity of the ball is going to have an I component and a j component. We take the square root of the sum of the squares, and we find that the actual speed of the ball is going to be 70.7 miles per hour, going at an angle of 45 degrees. So we'll get used to doing this I and j kind of concept, making sure that we understand the actual speeds, the relative speeds, and since they're both vectors, we'll have I and j components of both of them. So here's what we say. We're going to say the velocity of the ball has an actual speed and direction, the velocity of the car has an actual speed of the direction, and the velocity of the ball with respect to car is relative one to the other one. All right, so here's our procedure. Establish the vector equation. Velocity of A is equal to the velocity of B plus the velocity of A with respect to B. Make sure that these are all vectors, making sure that you understand that they have I and j components. These are the actuals. VA and VB are the actual speeds and directions of A and B whereas VA with respect to B, or if you had it the other way around, V of B with respect to A, those are the relative terms. So to proceed, we find out what you know, and usually that's given in the problem description. It could be the actual or the relative, depending on how the problem is worded. And you set up the equation. You have make sure all the terms are there, containing I and j components. Sometimes you'll have, most of the time, you'll have cosines or sines to deal with. You equate the pieces of the I and j into two equations, and then we solve for the unknowns. And we're going to do a couple of examples here. This is very similar to having in statics where we had some of the forces equal 0, but some of the forces may include i's and j's, and you separate out the forces such that you say the sum of the forces in the x equals 0 and the sum of the forces in the y equals 0, and you set up two equations. We're going to do exactly the same thing with velocities. So a couple of different things we're going to address here is we're going to have one object moving relative to a moving background, like wind or a river, or we could have two objects moving relative to each other, like we just showed with a moving car and a moving ball, or we could have two airplanes moving toward each other, or we could have three objects. We could have two moving objects relative to a third moving object, and we're going to analyze all those. All right, here's another example of a couple of objects moving relative to each other. Let's say that we have a car going in this direction at 20 meters per second. And at the same time, let's say there's another car up here going at a different speed. And let's say that he's going this way at velocity of b is equal to 23.09 meters per second. Let's say he's going at some angle here relative to the horizontal of 30 degrees. So if that angle is 30 with the horizontal, then this angle is 30. And we want to find out what the velocity of B looks like to the people in car A. So this is going to go this way and they're going to go that way. What do they look like relative to each other? All right, so let's set up our vector equation. We're going to say that the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. Those are all vectors. Well, we've got some equations. This is what we're looking for. This is our unknown. If I'm standing in A or sitting in A, what does velocity of B look like to me? B with respect to A. So let's say that the velocity of B is equal to 23.09. It's got some direction associated with that. It's going to be a cosine in the I direction. Let's make sure we establish plus and minus coordinates. So I'll say that this is my x and that's my y. So I got 23.09. I'll say that that's the minus cosine of theta in the I direction. Plus the, actually it's a negative sign as well. In other words, this is the x direction and this is the y direction. So it'd be negative sine theta in the j direction. And that's the only thing I have on that side of the equation. On this side of the equation, I got the velocity of A, which is equal to 20 meters per second, and that's going in the negative I direction. So that's negative I, plus the velocity of B with respect to A, which is what we're looking for. That's our unknown. Okay, let's multiply this out. And we're going to say that this is going to be equal to minus 20 in the I direction, minus 11.54 in the j direction. That's equal to minus 20 I direction, plus velocity of B with respect to A. And we established that the velocity of B with respect to A has I and j components. And that's built into that when I still leave the vector bar on the top. So let's do our i's first. I's. I'm going to say we have on this side of the equation, what I do is I equate the i's on one side of the equation to the i's on the other side of the equation. So I'll put in minus 20, which is that term right there. That's a j. So then I go equals. Then I got a minus 20 here, plus the velocity of B with respect to A in the I direction. Well, you can see that that cancels, so that's a 0. So I'm going to say velocity of B with respect to A in the I direction is equal to 0. That's my first conclusion. How about the j direction? Well, I've got minus 11.54 in the j direction is equal to, that's the I term. So I got velocity of b with respect to a in the j direction. So I can say that velocity of b with respect to a in the j direction is equal to 11.54. All right, what's my conclusion here? It says that there's no I component relative to me, which means it's not moving any faster than I'm going in the I direction. However, there is a j component that's coming straight at me. So if I'm looking out the window here, I'm not noticing that I'm moving in this direction. I'm not noticing that he's moving in this direction. All I see is B coming straight at me with 11.54 meters per second speed. So that's kind of the way you get started at the relative kind of thing. If I'm looking out the window of A, what does the velocity of B look like to me? That's what the B with respect to equation looks like. So here's an illustration of another illustration of a couple objects moving relative to each other. Let's say that this car is moving in this direction at 35 feet per second, and there's a boy over here that can throw a ball at 60 feet per second. And what he's going to try to do is throw it such that the passenger of the car catches it, or he's going to try to throw it through the window here. All right, we know that if he tries to fire it this direction, the car will have been in a different spot by the time the ball gets there. So we know just intuitively that he has to fire up at some angle up there in order to be able to hit the car. All right, so we're going to say that is his actual direction and his actual speed. So I'll go ahead and put actual here. And what we're going to try to do is establish that theta, that direction, to find out how he can hit the car. All right, since we also know that the car is moving in that direction, I can say that VA is actual in that direction as well. Actual. All right, let's also establish our coordinates and make sure we keep our x's and y's straight. So we'll do that. All right, now let's set up our vector equation. We know that the velocity of A is going to be equal to, it's going in that direction, so we said it's going at 35, so it's going to be 35 in the j direction. The velocity of the ball, we know its actual speed. Let's go ahead and put vector signs on that. The velocity of the ball actually is going up that direction. We know he can actually throw it at 60 feet per second, so I'll go ahead and put 60, and then let's put our directions in here. So we have a cosine component in that direction. That would be negative x, so minus cosine of theta in the I direction. Then he's got a positive sine direction, so a plus sine theta in the j direction. So there's our two actuals. The relative, we don't know for sure, but let's go ahead and put velocity of the ball with respect to A. What we do know is that we want to hit the car. So we do know that we don't want any relative j, since I'm at the same level here when I fire it. I don't want any relative j component. So what I'm going to say is that I only want there to be an I component when I get done with velocity of b with respect to a. If there's a j component, when it gets up here, it would be in a different spot. So I'll say that the velocity of b with respect to a is equal to some magnitude of b with respect to a in the I direction only. All right, now let's set up our vector equation and see what we can find. Let's velocity of the ball is equal to the velocity of the car plus the velocity of the ball with respect to the car. Each of those are vectors. So I've established the velocity of the ball. I'm going to say that is 60. And I'm going to say minus 60 cosine of theta in the I direction plus 60 sine theta in the j direction is equal to the velocity of the car is 35j plus the velocity of the ball with respect to the car in the I direction. That's the only component I've got. So now we combine our i's and j's, and let's see what we can get to solve for the angle theta. Let's try our i's first. We got do this side of the equation, then we do that side of the equation. So I'll say minus 60 cosine of theta in the I direction. That's that piece. That's a j component. This is a j component, and this is the I component. So VB with respect to A. Those are my two I pieces. I don't know that, and I don't know theta, so I can't really solve for anything there. Let's try j's and see what we get. So I'll say 60 sine theta is equal to 35. Hey, now I got something here. I can say that theta is equal to the sine minus 1 of 35 over 60, which is equal to 35.7 degrees. All right, so found my first answer. What is the angle that I have to fire at? Turns out in this case, I didn't need this equation. Sometimes it's simple enough that you don't need both equations, but in this case you didn't. All right, the next piece of the puzzle is how long does it take to hit the car? Well, it is actually going in this direction at 60 feet per second. And so if I knew this total distance, I could divide that by 60 and find out what the time was. So let's do that. Now that I know the angle, I can say the distance that the ball travels is this distance. So d is equal to, here I got a cosine here, so it's going to be 50 over the cosine of that angle. So it's 50 over the cosine, 50 over the cosine of 35.7. That's the distance it actually goes, and that's equal to 61.57 feet. And I know that the velocity, the distance that it travels, is actually the velocity times the time. So the time can be resolved by saying that it's 61.57 over 60. That's equal to 1.026 seconds. All right, I guess that's my answer right there, not that D part over there. All right, that kind of gets us a little picture of that. We could also find out what the time was by saying that there's a J component that has to travel this way at 60 feet. So I could say that 60 cosine of theta is equal to 50 feet, and you can find the time that way as well. Okay, let's do one more. This one is two moving objects relative to a third moving object. And what we've got here is we have an aircraft carrier moving in this direction at 50 kilometers per hour. It says that this aircraft has taken off and it is going at 200 kilometers per hour, and it says measured from still water. So that is the actual speed is 200. This guy B is taking off, and his speed is relative to the actual carrier, and it says that he's going at 175 kilometers per hour relative to the carrier. And we want to try to find out the velocity of A with respect to B. So if I'm standing on B, what does A look like? What does the velocity of A look like? All right, so first let's establish our axes. So I'll say that that's going to be my X and my Y. And let's say that, let's start with the velocity of A. Let's say the velocity of A is equal to the velocity of the carrier, plus the velocity of A with respect to the carrier. Now I know the velocity of A is going to be 200, and that's going in straight out in the I direction. We know the velocity of the carrier is also going straight in the I direction, so that's 50 in the I direction, plus the velocity of A with respect to C. So we can solve that A with respect to C is equal to 150 in the I direction. Now I'm not sure if I'm going to need every piece of the puzzle, but we're going to write them all down and see which ones end up getting in the equation. Since I have to go through carrier in order to find out the A with respect to B, since I wasn't given enough information to go directly there. How about V? So let's say the velocity of B is equal to the velocity of the carrier plus the velocity of B with respect to the carrier. Now this is what was given to me in the problem. So I'm going to say that the velocity of B is equal to 30I. That's what the carrier is, 50I. So 50 in the I direction. The velocity of B with respect to the carrier, it said I'm going 175 at the angle shown. So I'm going to say that that's 175. And it's going to have a cosine component, cosine of 15 in the I direction, and a sine component, sine of 15 in the J direction. All right, so there's my velocities there. And I can combine those two, and I can say that that is equal to 219.0 in the I direction plus 45.3 in the J direction. All right, I'm looking for the velocity of A with respect to B, but I think I've got enough information now. I can probably write down the equation. I'm going to say the velocity of A is equal to the velocity of B plus the velocity of A with respect to B. Again, I know what the velocity of A is, and I know what the velocity of B is, which I just solved for. So here's our unknown. So I'll say the velocity of A with respect to B is equal to the velocity of A, which is 200 in the I direction, minus the velocity of B, so it'd be minus 219.0 in the I direction, minus 45.3 in the J direction. Combining that is equal to minus 19 in the I direction, minus 45.3 in the J direction. Okay. If I want to find out the magnitude, I take the square root of the sum of the squares. So AB mag is going to be equal to the square root of 19 squared plus 45 squared, and that's equal to 49.12 kilometers per hour. That's the relative speed. And the relative direction, you kind of look at the picture and our components here to find out. So we know that the A relative to B has this kind of a component. It has minus 19 in the I direction, minus 45 in the J direction. So here is velocity of A relative to B, and you do the inverse tan here and you can see that this is equal to 67 degrees, like that. Anyway, that'll give you a little picture of how we get started on these relative problems. Thank you.